Hello everybody, welcome into another lesson. So today we are going to talk about solving exponential equations. So I've decided to split the exponential equations lessons and the logarithmic equations lessons into two separate lessons because there's a lot of ground to cover in each one. So let's get started here. So you have here a simple one like 4 to the x equals 16. Of course, the idea is through all this, we want to find the value of the variable. So you have an exponential equation you want to solve for x. And by inspection, you're probably saying that 4 to the x, that you could say that equals 4 to the second, you would get x equals 2, which you would be correct. But let me show you the proper full way to do this. So whenever you have a base to a variable power, what you have to do is take the log base of that base. So to solve for x, you would take log base 4 of 4 to the x. But what you do to one side, you got to do to the other. That would equal log base 4 of 16. Well, we know with the logarithm you have the power rule, so you can bring that x down front. You would have x times log base 4 of 4 is equal to log base 4 of 16, which is 2. Log base 4 of 4 is 1, so you'll just get a value of x equals 2. So that's how you really solve exponential equations. I should probably get an eraser. Alright, here we go. We'll solve another similar type. We have 5 to the x equals 1 over 625. So we've been given 5 to the x equals 1 over 625. So the base with the variable is 5, so we have to take log base 5 of both sides. So we'll take log base 5 of 5 to the x. We'll set that equal to log base 5 of 1 over 625. Well, on the left side you have a power rule, so that x would come down front. You'd multiply it by log base 5 of 5. Now on the right side, 5 to what power equals 625? 1 over 625 rather. That'd be negative 4. And then on the left side, log base 5 of 5 is 1, so you'll literally just get that x equals negative 4. Alright. We have 1 over 8 to the x power equals 64. So we have 1/8 raised to the x power equals 64. Well, it might be easier if we convert 1/8 into 8 to the negative first, right? So you could say this is the same as 8 to the negative first raised to the x power equals 64. Well, 8 to the negative first to the x power turns into 8 to the negative x, which would equal 64. Alright, now the base with the variable is 8, so we have to take log base 8 of both sides. So log base 8 of 8 to the negative x would equal log base 8 of 64. So on the left side, you got the power rule. That negative x will come down front, so you'll have negative x log base 8 of 8, which would equal log base 8 of 64, which is 2. So this would just turn into negative x equals 2, giving you that x equals negative 2. So the answer this time is x equals negative 2. Alright, so we have 2/3 raised to the x power is going to be set equal to 81 over 16. Well, what we have here, we know you can multiply 2 and get 16, 3 and get 81, but the problem is with this, your respective factors of 81 and 16 are reversed from numerator and denominator. So it very well may be helpful to you to write this 2/3 to the x as 3/2 to the negative x power and set that equal to 81 over 16. Now we got something we can work with. Alright, so let's take the log base 3/2 of 3/2 to the negative x. Set that equal to log base 3/2 of 81/16. Well, on the left side, that negative x will come down front. This will be negative x times log base 3/2 of 3/2 would equal the right hand side. 3/2 to what power equals 81/16? That would just be the fourth power, so the right hand side would just become 4. So on the left hand side, this reduces to negative x equals 4, which would give you that x equals negative 4. So the answer you should get for this one is x equals negative 4. Okay, interesting one here. So we have 6 times the quantity of 10 to the x power equals 216. You can have multiples on logs. That can completely happen. First thing you want to do is isolate that 10 to the x by itself, so divide both sides by 6. You'll end up with 10 to the x equals 36. Now you got a form you can work with. So the left side you have 10 to the x, so you got to take log base 10 of both sides. So log base 10 of 10 to the x is going to equal log base 10 of 36, which the left side would turn into x times log base 10 of 10 would equal log base 10 of 36. So the left side, you'll get x equals log base 10 of 36, which that's the exact solution as log base 10 of 36, but here's the problem. 10 doesn't go into 36 by any even power. So we're going to definitely keep the exact solution, but we also need to get a decimal solution to approximately 3 decimal places. So on your calculator, that would just simply be log, because again, those are set for the common logarithm of base 10. So log of 36 gives you about 1.556. So my exact solution is x equals log base 10 of 36. My approximate solution is 1.556. And that might be useful if you're graphing or trying to figure out other things, but it's just good to show you how to approximate. Now, how about something like this? You have 2 to the x plus 3 equals 256. So you have 2 to the x plus 3 power equals 256. Well, still, you have the variable in the exponent with a base 2. So you're going to take log base 2 of both sides. So log base 2 of 2 to the x plus 3 power would equal log base 2 of 256. So on the left side, that x plus 3 would come down front. That'd be the whole x plus 3 times log base 2 of 2. That's going to equal your right-hand side. So let's see. 2 to what power equals 256? That'd be 8. So on the left side, this would just turn into x plus 3 equals 8, which should give you that x equals 5. So the answer you should get for this one is x would equal 5. Now we're going to get into some harder exponential equations here. So we have 8 to the 3x power equals 360. Well, again, your base is 8 with the variable, so you're going to want to take log base 8 of both sides. So log base 8 of 8 to the 3x would equal log base 8 of 360. Well, the left side, your exponent will come down front, so you would get 3x times log base 8 of 8. That's going to equal your right-hand side. Well, with logarithmic expressions, you want to simplify as much as possible. Just like if you were to get a common denominator in a fraction or rationalize the denominator of a rational expression, it's the same sort of idea with logarithms. You want to get this to be as simple as possible for the exact solution. So let's see if there are any factors of 360 that contain 8. And there actually turn out to be. 360 has factors of 8 times 45. So the left-hand side would just turn into 3x. The right-hand side, you would get log base 8 of 8 plus log base 8 of 45. Which then means that 3x is going to equal 1 plus log base 8 of 45. So x itself is going to equal 1 plus, it'll equal 1/3 plus log base 8 of 45 over 3. So that would be your exact solution for x, is x would equal 1/3 plus log base 8 of 45 over 3. But we can get algebraic approximate solutions too. So we need to figure out a way to round this to 3 decimal places. Well, that log base 8 of 45, we're going to have to use the change of base formula. So what I'm going to suggest here is we're going to keep the 1/3. X is going to equal 1/3 plus 1/3 times, now we got to deal with that log base 8 of 45. Let's say the natural log of 45 over the natural log of 8. And then we can get an approximate solution. Which would give you about 0.944. So if you're looking for a decimal, you would get approximately 0.944 by the time you input all that into your calculator. So the exact solution is x equals 1/3 plus log base 8 of 45 over 3. The decimal approximation is about 0.944 if you're rounding to 3 decimal places. All right. So we have 5 to the negative x over 2 equals 0.20. Well, so we have 5 to the negative x over 2 equals 0.20. It might help to rewrite the right-hand side as a fraction. So this would be 5 to the negative x over 2 equals 1/5. Now we have something we can work with. So the left side has the variable, so we need to take the log base 5 of both sides. So take log base 5 of 5 to the negative x over 2. That's going to give you log base 5 of 1/5. So on the left side, this would become negative x over 2 times log base 5 of 5. That would equal your right-hand side, which would be negative 1. So you would end up getting negative x over 2 equals negative 1. So negative x would equal negative 2, which would have to then mean that x equals 2. So it looked hideous at first, but you end up getting a simple solution that x equals 2. Good one. So we have 5 times the quantity of 2 to the 3 minus x minus 13 equals 100. All of a sudden, this is not so nice. Well, we definitely want to start out by getting that 5 times 2 to the 3 minus x by itself. So this will turn into 5 times 2 to the 3 minus x is equal to 113. Next, we get the 2 to the 3 minus x by itself. So you would end up getting 2 to the 3 minus x equals 113 fifths. And I can tell you right now, 2 doesn't go into any of these numbers evenly whatsoever. There won't be any factors that are going to work. But nonetheless, take log base 2 of both sides. So you'll end up getting log base 2 of 2 to the 3 minus x. That's going to equal log base 2 of log base 2 of 113 over 5. So on the left side, this would become 3 minus x times log base 2 of 2 would equal log base 2 of 113 over 5. So then you would just have 3 minus x equals log base 2 of 113 over 5, which would then give you that x equals exactly 3 minus log base 2 of 113 over 5. That would be for your algebraic exact solution, is that x equals 3 minus log base 2 of 113 over 5. But you know what time it is? Yes, we have to come up with the decimal solution. So you could say that x equals 3 minus the natural log of 113 over 5 all over the natural log of 2, which should then give us our decimal approximation. Alright, so then we take 3 minus that answer. You get about negative 1.498. So to 3 decimal places, you get that x equals approximately negative 1.498. So what a doozy to obtain all that, right? Alright, change it up again a little bit. So we're going to have 1 plus 0.10 all over 12 raised to the 12t power set equal to 2. So this is not going to be fun. So we have 1 plus 0.10 all over 12. That whole quantity raised to the 12t power equals 2. So we're going to follow order of operations first. So work inside your parentheses. So let's figure out about what that would be. Try to get it exact if we can. So you get approximately 1.008, which would be raised to the 12t power set equal to 2. So this is not really pretty, but that's what it is by the time you did all the work in the parentheses. Now, your base is 1.008, and then your exponent's 12t. So you got to take the log base 1.008 of 1.008 to the 12t, set that equal to log of 1.008 of 2. So the left side, you'll end up just getting 12t equals the right hand side, which would be log base 1.008 of 2. So t is approximately equal to log base 1.008 of 2 divided by 12. That's the approximate algebraic solution. But now we got to try to figure out the decimal solution to 3 decimal places. And again, this is not going to be exact. If you were doing this in a textbook, your answer might vary by a tenth or so, but that's okay. I mean, as long as you're in the ballpark and not off by a lot. So the numerator would end up becoming, well, actually this would be helpful to write it as 1/12 times the natural log of 2 all over the natural log of 1.008. Now we should be able to proceed to getting our decimal solution. So you get about 7.249. So that t is approximately equal to 7.249 for your decimal places, for the decimal solution. What do I got? I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 10 more left, but they're all very important. So we have 5,000 times 1 plus the quantity of 0.005 raised to the x power. Oh, it's the whole quantity. I thought it was, I don't know why I did that. All over 0.005 is equal to 250,000. So this one looks like a bit of a doozy. So you have 5,000 times the quantity in brackets of the quantity in the numerator of 1 plus 0.005 raised to the x divided by your denominator of 0.005, all equal to 250,000. Well, I think it's safe to say we want to get the brackets by itself, so divide both sides by 5,000 and it should already start to simplify. So 250,000 divided by 5,000 would give you 50. So this would turn into 1 plus 0.005 to the x over 0.005 equals 50. Much easier to work with. Now, of course, you probably want to get that numerator term by itself. Let's do a couple things. Let's simplify the parentheses in the numerator. This is going to end up becoming 1.005 raised to the x power. And then we're going to multiply both sides by that 0.005. So let's take that 50 times 0.005. You get 0.25. Alright, so now we got it in a form we can easily work with. You have 1.005 to the x equals 0.25. So we're going to take the log base 1.005 of that 1.005 raised to the x power. We're going to set that equal to log base 1.005 of 0.25. So the left side would just become x, and for your exact solution, that's what you're going to be left with on the right hand side, log base 1.005 of 0.25. That is going to be your algebraic exact solution. Now, what about an approximate solution? So x would equal the natural log of 0.25 divided by the natural log of 1.005, which now we can take a decimal approximation to about 3 decimal places. So you get approximately negative 277.951. What a messy power that is. So you get approximately negative 277.951. What a solution. All right. This one won't be too bad. You have 2e to the 5x equals 18. That one's a little bit tamer. So you have 2e to the 5x equals 18. Well, we definitely want to get that e to the 5x by itself, right? So this would become e to the 5x equals 9. Now you have base e, so you have to take the natural log of both sides. So this would turn into natural log of e to the 5x equals the natural log of 9, which would mean 5x equals the natural log of 9. So x would equal exactly the natural log of 9 divided by 5. That's the exact solution. And then we can get a 3 decimal place approximation for it. Which would give you about 0.439. So x equals exactly the natural log of 9 divided by 5, or approximately 0.439. All right, that one wasn't so bad. All right, let's see. 500 e to the negative x equals 300. So we definitely want to get that e to the negative x by itself, so this would just turn into e to the negative x would equal 3/5. So you have a base e to the negative x, so you take the natural log of both sides, so the natural log of e to the negative x equals the natural log of 3/5, which means you would get negative x equals the natural log of 3/5, which would have to mean then that x equals negative of the natural log of 3/5, which actually means this would be the same as the natural log of 5/3. because that -1 on the natural log, that becomes a power rule, and 3/5 to the -1st is 5/3. So x would equal exactly the natural log of 5/3. Now we can get an approximate solution to this. So let's see here. You get approximately 0.511. So x would equal exactly the natural log of 5/3, or approximately 0.511. All right. 7 minus 2 times e to the x equals 5. So 7 minus 2 times e to the x equals 5. Alright, well, we want to get that -2e to the x by itself, so this will end up becoming -2e to the x would equal -2. Then we want to get the e to the x by itself, so that's just going to end up being e to the x equals +1. So now take the natural log of both sides. Natural log of e to the x equals the natural log of 1, which would just give you that x equals 0. So you end up getting a big fat 0 for your value of x. Now this is going to be interesting. We have a quadratic exponential equation. So you have e to the 2x minus 4e to the x minus 5 equals 0. So you have e to the 2x minus 4e to the x minus 5 equals 0. You can treat this like a quadratic equation. Or if this helps you, here's something you can do. We can use what's called a u substitution. What do I mean by that? So let u equal e to the x. So here's what's going to happen. This will end up becoming, so e to the 2x, if you're making u e to the x, that's the same as u squared. So this will turn into u squared minus 4u minus 5 equals 0. Now you temporarily have a very simple quadratic equation. So this, of course, would factor into u plus 1 times u minus 5, which would equal 0. So set each of these equal to 0, you would get u equals -1 and u equals 5. But when you do the substitution, you have to put your original value back from the substitution. So that u is really e to the x. So we're saying that e to the x equals -1, and then we're also saying that e to the x equals 5. Well, let's look at e to the x equals -1. Does e to any number equal a negative number? Never, right? Never. So that would be considered an extraneous solution, because you would end up with the natural log of -1, which is undefined. But e to the x equals 5 is defined, so take the natural log of both sides. Natural log of e to the x equals the natural log of 5, which would just give you then that x equals the natural log of 5 for the exact answer. And then we could get a 3 decimal place approximation. All right, natural log of 5, 1.609. So you get that x equals approximately 1.609, or exactly the natural log of 5. So you can get extraneous solutions when trying to solve these. Alright, let's see. 250 times e to the 0.02x equals 10,000. So 250e to the 0.02x equals 10,000. Well, we definitely want to get that e to the 0.02x by itself. So you just divide both sides by 250, you would end up getting that e to the 0.02x would end up equaling 40. Much easier to work with now. Now just take the natural log of both sides, so it'll be the natural log of e to the 0.02x equals the natural log of 40, which would just give you that 0.02x equals the natural log of 40, which would end up giving you that x equals exactly the natural log of 40 over 0.02. That's the exact solution, but what about a decimal approximation? Let's go ahead and find that. Alright, so natural log of 40, divide all that by 0.02, you get 184.444 for your approximate solution. So x would equal exactly the natural log of 40 divided by 0.02, or approximately 184.444. And I have 4 more problems. So we have e to the x equals e to the x squared minus 2. So now you have the same base on both sides. Well, you're still going to take the natural log of both sides. So this would end up being the natural log of e to the x equals the natural log of e to the x squared minus 2, which would end up just meaning that x equals x squared minus 2. Now you just have a simple quadratic equation. So you end up getting x squared minus x minus 2 equals 0, which would factor into x plus 1 quantity times x minus 2 quantity equals 0. So this is, let's see here, yep, so you would get that x equals negative 1 and 2. Let's just make sure we don't have an extraneous solution. You don't, they both check. If you put each x value in, the left side matches the right. So you actually have 2 solutions here where x equals negative 1 and 2. Got 3 more. We're coming down to it. Alright. E to the x squared minus 3x equals e to the x minus 2. Alright, so e to the x squared minus 3x equals e to the x minus 2. Alright, so we're going to have some fun with this one. So let's take the natural log of both sides. So the natural log of e to the x squared minus 3x equals the natural log of e to the x minus 2, which would turn into a simple quadratic equation. You would end up getting that x squared minus 3x equals x minus 2, which would simplify then into x squared minus 4x plus 2 equals 0. Well, sadly, this isn't going to factor. It just isn't going to factor. So what I would suggest is we use the method of completing the square to solve this. So let's make this x squared minus 4x equals negative 2, which would turn into x squared minus 4x plus 4 equals negative 2 plus 4. So then you would end up getting the quantity of x minus 2 squared equals positive 2. So then you're going to end up just getting x minus 2 equals both plus and minus the square root of 2, which for the final answer would give you that x equals 2 plus and minus the square root of 2, and we're going to have two solutions. So those were your exact solutions. Now let's find decimal approximations. So let's do 2 minus the square root of 2. So your first decimal approximation would end up being approximately 0.586. Your second one, we're going to do 2 plus the square root of 2, which would be about 3.414. So your two solutions are going to end up being x equals approximately 0.586 and approximately 3.414. All right. We have two more that both involve extraneous solutions. So we have 400 divided by 1 plus e to the negative x, which would equal 350. What do I mean by extraneous solutions? Well, we have to look at the denominator. Is there a chance the denominator could equal 0? Well, that would have to mean that e to the negative x would equal negative 1, which we know isn't possible. So there won't be any extraneous solutions this time. So this would turn into, we want to get this out of the denominator, so this would turn into 350 times the quantity of 1 plus e to the negative x, would simply end up equaling 400, which would give you that 1 plus e to the negative x would end up equaling, let's see, 8/7, which would end up giving you e to the negative x equals 1/7. Much easier to work with. Now we just take the natural log of both sides, so the natural log of e to the negative x equals the natural log of 1/7. So negative x equals the natural log of 1/7. that means x equals negative of the natural log of 1/7. But that negative 1 in front of 1/7, the negative 1 in front of the natural log would make this a power rule. So that 1/7 would become to the negative first power. That means x really equals the natural log of 7, which then we can get a decimal approximation. So the natural log of 7 is approximately equal to 1.946. So x equals exactly the natural log of 7 and approximately 1.946. And we got one more problem, then we're done. Now, this is going to be interesting because this next one could possibly give us an extraneous solution. Let's show you what I mean here. So we're going to have 40 divided by 1 minus 5e to the negative 0.01x. All that is going to be equal to 200. Alright, so we got to look at the denominator. Is there any chance the denominator could equal 0? Well, let's set the denominator equal to 0. So you'll end up having 1 minus 5e to the negative 0.01x equal to 0, which would mean that 5e to the negative 0.01x equals 1. So yes, there is a possibility you could get some number that equals 1, which would make the denominator 0. So in other words, we're going to try to find the extraneous solution so we know to stay away from it. So this would turn into e to the negative 0.01x equals 1/5, which would mean that negative 0.01x is going to end up equaling the natural log of 1/5, which means that 0.01x is going to equal the natural log of 5. So then x would equal the natural log of 5 divided by 0.01. That is going to be the extraneous solution. So we want to specify that x cannot equal the natural log of 5 divided by 0.01. So you see how I got that extraneous solution. If we get that for an answer, we're not going to have a solution. So x cannot equal this, otherwise your denominator becomes 0. Now the real work begins of solving this. So to solve this, you want to get this expression out of the denominator. This would end up becoming 200 times the quantity of 1 minus 5e to the negative 0.01x equals 40, which would turn into 1 minus 5e to the negative 0.01x equals 1/5. So then you would end up with negative 5e to the negative 0.01x is going to end up equaling negative 4/5. So then you would get that e to the negative 0.01x equals positive 4/25. Much easier to work with. So now we just take the natural log of both sides. So this would just give you negative 0.01x equals the natural log of 4/25, which would give you that 0.01x equals the natural log of 25/4. So x is going to equal the natural log of 25/4 all over 0.01. So at the very least, we did not get an extraneous solution. So that's a very nice thing. We didn't get the extraneous solution. But now let's figure out what the heck that is to a decimal approximation. You get approximately 183.258. Whoops, not that. There we go. 183.258. So x equals approximately 183.258, or exactly the natural log of 25/4 over 0.01. What a doozy. So that's it for this lesson. Next lesson, we're going to work in reverse. We're going to solve logarithmic equations. So I hope everyone has a great day. Take care.